All right, so we were talking about recording or collecting, gas over water, and this is something that we will be doing in one of our upcoming labs. So we'll have something similar to this setup. It won't be a beaker that's upside down, but it will be an upside down glass container that will be filled with water, and we'll be collecting hydrogen gas in the top of the container, and that's going to force water out. The pressure of the gas on the inside of this container is going to be the same as the atmospheric pressure on the outside. So by checking with our little device on the wall, we can check what the atmospheric pressure is in the room, and we can figure out what the pressure is inside of that container. Then using that, along with a table sort of like this, where we've got the temperature of the water and the vapor pressure, we can figure out what the pressure of the gas is inside of that container. We can also do other fun stuff with the ideal gas law in particular, like things with stoichiometry. So if we have a gaseous reactant or product, then we can sometimes specify the amount of gas at the volume with given temperature and pressure using our ideal gas law. So rather than having grams as our starting amount, we might be given pressure, volume, and temperature instead, and we can use those values to get to moles. Since we know that PV equals nRT, we can start with pressure, volume, and temperature and go to moles of another thing, and then to maybe grams, or if it's another gas, we can go to pressure, volume, or something else. So let's look at what some of those calculations might look like. Sulfuric acid is one of our most prepared chemicals in the United States, as it turns out. One of the uses that you might see around here especially is like if you pass by a blueberry field, if you happen to see blueberries around here, there are blueberry growers. Sulfuric acid is often used to acidify the soil, since blueberries need acidic conditions to grow. So they'll have giant tanks of this stuff that they feed through their drip lines. You can also use it to descale your drip lines or to keep them from getting hard water deposits and jamming up. That being said, this is a reaction used to prepare sulfuric acid H2SO4. So we want to know what volume of oxygen in liters, how many liters of oxygen gas under these conditions, 22 degrees Celsius, 745 millimeters of mercury pressure, is required to produce 1 ton of sulfuric acid. And 1 ton is about 907 kilograms of sulfuric acid. So the unit that we're going to be starting with here is the kilograms of sulfuric acid, since we're asked to find volume of O2. So to start off, 107.18 kilograms, we'll want to convert that into grams. So times 1,000 grams per 1 kilogram, 907,180 grams of H2SO4. And we know that we can turn grams into moles. We'll need a molar mass. So we can calculate that. Doing that here in the blue. So add all of those things up together, and that should give us our molar mass of sulfuric acid. Our molar mass for sulfuric acid is 98.018 grams per mole. We're going to have a lot of moles of sulfuric acid, since we have a ton, literally, of sulfuric acid. So dividing by our grams per mole, (9,255.2 ... moles of sulfuric acid. That is a lot of moles. What can we do with moles of sulfuric acid here? Yeah, we can convert from moles of sulfuric acid. All right, we just got moles of sulfuric acid. Our other thing that we might do, right, oftentimes we're taking moles and turning it into grams, but we just came from grams, so that's not going to be it. So we can convert the sulfuric acid part of this. We have a balanced equation, and this tells us that we produce 2 sulfuric acid molecules for every 3 oxygen molecules we put in. And that also applies for moles of those substances. So we'll produce 2 sulfuric acid, moles of sulfuric acid for every 3 moles of O2. We can make our conversion factor out of that ratio. So we would need 3 O2 for every 2 H2SO4 that we produce. So that'll convert us into moles of oxygen. Even bigger number. Over 13,000, almost 14,000 moles of oxygen. I'm going to shrink that calculation to give myself some room. We are trying to find volume. So for volume, we can take our ideal gas law and solve for V. So PV equals nRT. We'll turn that into V equals nRT over P. R is our ideal gas constant, and T and P need to be in the correct units for our ideal gas constant. So we're going to add 273.15 to our temperature. We need to be in kelvins for temperature, and we'll convert millimeters of mercury to atmospheres. So that they match up with our units in the R value. And we can plug everything into this V equals nRT over P, and we'll get our volume of oxygen. It should also be a really large number. So our moles times our gas law constant times our temperature in Kelvin Kelvin and moles will cancel, and that's all over our pressure. So pressure also cancels. We'll be left with liters, and it's going to be some ridiculously large number. And that number is 343,180 liters. And we'd probably round it to 3 sig figs. And just for fun, we'll make it kiloliters, even though I don't think anyone uses kiloliters. So 343 kiloliters. Questions about any of the steps that we did there? So we're pairing stoichiometry, which we've seen previously, with ideal gas law stuff. So we've got new options for chemical reactions that we can do. Another thing that you'll sometimes see is what's called standard temperature and pressure. So standard temperature and pressure, I don't know who set STP, but that's what STP stands for. STP is 0 degrees Celsius and 1 atmosphere of pressure. So the standard temperature is freezing cold for water, and at 1 atmosphere, so sea level. So you're freezing cold, but you're by the ocean, so it's nice. That's STP for you. We can calculate the volume of 1 mole of gas at standard temperature and pressure. V equals nRT over P, like we saw earlier. If we put in 1 mole times 0.0821 latum per molk times our 273 Kelvin divided by our pressure of 1 atmosphere, we get a bunch of stuff to go away. And the one on top and the one on bottom, we can just ignore those. So 273 times 0.0821, this will come out to right about 22.4 liters. Basically, the only time that this is convenient is that it's really quick. If we're at or near standard temperature and pressure, we can do really quick volume estimates for moving between liters of a gas and moles of a gas. And it works decently well also at like room temperature, so conditions that we are likely to be in. You can just kind of estimate based on a volume, like there's approximately, however many moles of gas, or this many moles of gas would be approximately this many liters. Some of you may want to memorize that the molar volume of a gas is 22.4 liters per mole at STP. If you remember the conditions of STP, freezing cold at sea level, 1 atmosphere of pressure and 0 degrees Celsius, you can also come up with this 22.4 conversion factor. We could use that for a question like this. How many liters of nitrogen at STP are required to form 9.85 grams of ammonia? So the only number that we're given here is grams of ammonia, so that's going to be our starting point for our calculation. And we're going to liters of nitrogen. This at STP is a very helpful hint for us if we've got 22.4 liters per mole stored away in our brain. So go ahead and give that problem a try. All right, the starting point for this problem, as mentioned, are 9.85 grams of ammonia. What can we do with grams of ammonia? turn it into moles, also of ammonia. Once we get to moles of ammonia, what can we do? Yeah, turn it into moles of N2. For this first step, we need molar mass. For this second step, we need the ratio from our balanced equation. And what can we do from moles of N2? We can plug it into PV equals nRT. That's one option. Or if we have that 22.4 liters per mole stored in our brain, we are at STP, so we can use that 22.4 liters per mole as kind of like a shortcut to get to liters of N2. Questions about the solution map? Okay. Our molar mass, 17.031 grams per mole. Let's set up our calculation. 9.85 grams ammonia divide by our molar mass. So our grams cancel. Our units are now moles of ammonia, where we want to be, and we can convert to moles of N2 using our ratio of 2 to 1. The 2 goes on the bottom with the NH3 so that our NH3, our ammonia, cancels, and N2 goes on the top. So NH3 cancels. We've now got moles of N2, and since we're at STP, we can use this 22.4 liters per mole as a shortcut. The other option would be to use our PV equals nRT. They'll give you the same answer. So 22.4 liters for every 1 mole of gas. And our end units are liters of nitrogen gas. Should end up with 6.48 liters of N2. Any gas questions? That's the last slide for gases. Alrighty then.